Okay, so I'm going to try to talk about how to graph solutions to a system of differential equations. And the way I want to start is I want to say, suppose that the solution, oops, for some reason I've got a weird color there. Let me start with white. Okay, suppose my solution is of the form C1 e to the positive t times u plus C2 times e to the minus 2t times v. Okay, and now these two vectors u and v are our two eigenvectors. And so if we were to plot this, what we're thinking about doing is plotting this for different value, plotting the solution for different values of C1 and C2, right? It's just to get a visual sense for what's happening in the plane. So this is my x1 and my x2, and I need a u and a v. So I'm just going to draw, let's suppose that this is my v, and let's suppose that this is my u. Okay, so those are nice u's and v's. Now, I'm going to get rid of these this notation here, but that's where I'm starting. I want to get rid of the, oops, I'm erasing the whole thing. I want to get rid of the arrowheads too, because that kind of indicates a direction. Okay, so I'm going to just start with a u and a v that way. Okay, now if I start my solution anywhere on the u vector, right, that means that C2 is going to be equal to 0, right? And so which direction am I going to travel in time if I fix C1? So for example, oops, this might be C1 equals 1, this might be C1 equals 2, C1 equals 3, and so on. Right, so, oh, did I just, okay, I think I just reversed my u and my v. Okay, so I'm thinking of this as my u now. Sorry about that. I think I reversed those. Okay, so we'll take that to be our u. And so what happens over time then to our solution? Because of this exponential function, e to the t, and the positive exponent, our solutions are going to be going to infinity along this line, right? And so what happens now if I had started with a negative C1? So this would be like minus C1, this would be maybe minus 2 for my C1, and so on. So if I had started over on this side, then you can see this function is still growing without bounds, so I'm going to be moving away from the origin along that line. Good. Now, let's take a look at V now. And suppose that I start somewhere on this vector. Okay, so again, up here, this might be C2 equals 1, this might be C2 equals 2, this might be C2 equals minus 1, and in all cases, if I'm on that line, C1 is equal to 0. Okay, and so if I start anywhere on this line, let's start down here where C2 might be negative, where do I go as time goes to infinity? Well, that's all determined by this function, right? This is the only function in time, and so e to the minus 2t is going to 0, and so therefore you're going to be approaching 0 along this line, right? So if you start anywhere on this line, you're going to be approaching 0. So while we're here, it looks like geometrically that these lines are actually intersecting the origin. Is that true? It is not, because the origin is actually a separate solution. X equals 0 is an equilibrium solution. And so if you were to start at 0, you would not move anywhere. Okay, so it's only if you're away from 0, like if I started here, well, let me just write again. If I started here, right, I would move that direction. If I started here, I would move towards 0, but I would never hit it. Okay. Good. Okay, so this is what happens if we look only at u and only at v. Now suppose what happens now if I take a look at other points. So for example, suppose I start right here. Can you estimate values of C1 and C2 for that? Well, we probably have a little over 1 for C1 and maybe something close to 0 for C2, right? So C1 is bigger than C2 in that case, but in both cases they're both positive, number 1, and number 2, C2 is not 0. Okay, so C2 is actually something. And so then what happens to this whole expression then? Oops, why am I moving? As time goes to infinity. Well, we see that along V, did I say that right? Gosh darn it. Because I keep switching my axes on you. Sorry about that. V is associated with C2, and so C2 is going to be about a little bit over 1. So for this point right here, C2 is about 1, and then C1 is about 0. But it's not equal to 0. That's the important thing there. Okay, and so let's see where we're going to go from there then. So if I'm starting at this point, where am I going to go in my solution here? Well, this part of the solution is dropping to 0, and this part is going to infinity. Right, so therefore you're going to go to infinity along the vector u, and so what happens is you end up doing something like that. So notice that we're going to infinity alongside or parallel. It's going to be getting closer and closer to this vector as we go out farther and farther. Okay, and so you can see here, because if you hit this line, right, that means that your C2 part would be 0, actually 0. Okay, but we know that it's never going to actually be exactly 0 because of the exponential function there. Okay, and so solutions close by are going to do something similar then. They're going to go to infinity. And then similarly down here, can we estimate what C1 and C2 are down here? Let's see. C1 is this part of the solution, right? And C2, oh, am I doing this right again? This because this is my this is V, yeah, right. So C2 is like negative 1 in this case. C2 is getting close to 0. But if you look at the solution up here, you're seeing that the same kind of behavior is happening. This part, let me redraw that with red here. This part of the equation, this part of the solution, I should say, is going to 0 because of the negative exponential, and this part is going to positive infinity. And so therefore, I seem to have a ghost moving my picture around. This solution is going to look something like that. Okay, and then like that. Good. And then similarly, these solutions are going to come around like this. Okay. And so one question that you might have, by the way, the origin is called a saddle point in this case, a saddle. What I'm doing here is I'm classifying the origin, classifying the equilibrium, Yeah, in this case it's a saddle. Good. All right. And so for a saddle, we have different signs up here. One is a plus and one is a minus. And you notice that almost all solutions go to infinity plus or minus infinity. Can you name a solution that does not go to plus or minus infinity? Did you guess that if C1 is equal to 0 and C2 is anything, these solutions, if you stay right on these vectors, right, if you just stay right on those vectors, you're going to go right to 0. Those are the only solutions that are going to 0. All other solutions go to infinity, plus or minus. Good. Okay, so that's about 10 minutes. We're going to look at the same picture in the next video, and we're going to just change the signs, SIGNs, of the exponents, and we're going to get a completely different image. Okay, stay tuned for that.